Hello, Dr. Sengupta.
Hey, how are you, Erin?
I'm good. Bay and I are actually both in the classroom because we have a class right after this one.
Oh,
So we might have like sound going on one computer, but she's joining right now.
okay, that's fine. But there's another person there. Did you see him?
See who?
I think Tech. What is his name?
Taeyeon? No, he's not here. He is in our next class, but I haven't seen him
yeah.
yet.
Okay, all right. Good. So, how was the homework going on?
Good. I just turned in homework number 2.
You did turn in?
Yeah, I just turned it in.
Just did, okay.
Is it mine?
I think your mic's on.
It's, oh, hold on.
But did you take the test of understanding?
I have not taken that yet. I have not taken the quiz yet, but I am getting the assignments. Yeah.
Do you have any issue or anything? Oh,
I think it's just working through it. For me, it's been a while since I've done some of this math, or I don't know if I've ever done some of this math. So it's just learning about it. I was not an undergrad mathematics major, so
I see. Oh, that's
the
interesting.
last math class I took besides the grad courses I've taken was AP Calculus.
Oh, okay.
So, but it's going well.
Yeah.
Luckily, I'm teaching AP Calculus, so the unit circle is going okay, and the complex numbers.
Mhm. So Bay, right?
Yes.
Everything is okay with you?
Can you turn your volume up? What was that?
Everything is okay with you?
I'm sorry, my volume was off. What did you say?
I said everything is okay with you.
Yeah, everything's going okay so far. I just started homework assignment number 2,
Okay.
and I did I went over the PowerPoint and then took notes from the PowerPoint for the homework assignment number 2 and quiz 2.
Mm-hmm. Do you have any issue?
No, I'm understanding everything so far, so I think
PowerPoints are good. I
it's
mean, I developed those last year, I think, yeah. Last year or year before last. So I don't know what we should do today.
Yeah, I was wondering what you would like be discussing with us today, because I know both of us already went over the PowerPoint and the notes. So I didn't know if you were checking on our progress since we aren't able to meet in person.
I mean, I can teach my class, but it seems like you understood everything there. What I'm going to talk about today. Basically, I'm going to talk about the PowerPoint too.
Okay, yeah, I've understood everything so far for PowerPoint too. Yeah.
Yeah, maybe briefly I talk about 10-15 minutes. How about that?
Okay, yeah, that sounds good.
I just want you to get used with me. Because this is, as I said, this is a calculus class, right?
Mm-hmm.
It's like Erin's area, right? The calculus. This is a calculus with complex variable, right?
Right.
What do you do in calculus? I'm sorry. I mean, I this is my teaching style, so I ask question, get feedback, then I go on. So what do you do with calculus?
What do we do with it, or do in
Do in
calculus?
calculus.
I think Erin could better answer that question since she's teaching it, but I would say it's a lot of dealing with graphing and the unit circle, and
I'm gonna take over from there. So a lot of it in my class at least is finding like tangential lines and average rate of change or instantaneous rate of change, and then area under a curve.
Mhm.
But you're doing it for the I believe for the applications to physics and the idea of what is my velocity or my acceleration at a certain point.
Okay. Yeah. So the calculus you do you do take the derivatives, right?
Hmm.
Or you integrate them. So what do you integrate or take the derivative? The object is here is the function, right?
Hmm. So you take the derivative of the function to find the
Function.
slope at any one point.
The function, right?
Hmm.
Yeah. So here object is the function. So you have function, you take the derivative, you take the integration, right? Whatever that means, that's a different story, right?
Hmm.
But how do you integrate? How to differentiate? What does that mean, right? These are the
Hmm.
questions you answer in calculus, right?
Hmm.
Yes. So same thing I'll be doing here in complex analysis, that I'll have my object will be complex function, right?
Okay.
So I'll talk about that probably next week, by next class. But the object will be the complex function. And then question is, how do you take the derivative? How do you integrate this function, right? Because complex function have more room than one-dimensional function, which you do in Cal 1 and Cal 2, right?
Hmm.
But if you do the several variable, you have more room, right?
Hmm.
Like a single variable, you are driving in a car in a street, right?
Yes.
Then I gotta go one way or the other way, right?
Hmm.
What I mean by limiting, take the limit in one-sided, two-sided limit, right?
Exactly. Yes. You can only come to a point from either side.
When you do the two variable, you get more room in it, right? So that means you are in the boat in the ocean, right?
Hmm.
So two variables, right?
Hmm.
But if you do three variables, you are in the sky, right? In the plane, right? You have more room.
Okay.
The rooms
Hmm.
room or more room you are getting every time you're changing the number of variables, right?
Hmm.
But I think in last class, do you see my screen? No,
Yes.
the white screen, right?
Yes. With complex analysis on the top.
So Tian is here, Renault, right? Tian,
Yes, sir.
It looks like it. Yeah.
can you turn your video? So
Yes, sir.
I think I taught Tian some time back. Is it right? Yeah. Did I teach you before, Tian?
Yes, sir. You taught me cryptography.
Oh, cryptography, yeah. I remember sometime I taught you, but I don't remember exactly which class,
Mhm.
Okay, good. Nice to see you back. So I just want to give you an overview what we are doing, right? So basically we'll be doing calculus. So again, the object is function. This time we'll have a complex function instead of real function. And then we'll learn how to take the derivatives. We'll learn how to take the integrals. Since we have a more room, so integration is a little different than when you do it a real function in one-dimensional case. It's more similar to the function of several variable cases. Because as you saw my last instruction, let me just briefly talk, maybe not much. So my variable is z, right? And z has x plus I, y, right? It's nothing new to you, right? And so every complex number can be written as x plus I, y, where x and y are
Real numbers.
numbers, right? And x is called the real part of z, right? That's the real part of z. And y is called the imaginary part of z. Is that right? So by the way, this representation of complex number is called Cartesian representation. Right? Because you are using x and y as a Cartesian coordinate, right? So you can think a complex number, it's a number, but you can think a complex number is a point in the plane, right? So you can think the complex number in the point in the plane. So here is the Cartesian plane, and here is a point x comma y. So this is your x, sorry, I mean, this is your x, this is your y, and this is your z, which you can think as x plus iy, right? So every complex number, you can represent a point on the plane, right? And every point on the plane can be written as a complex number, is that right? So that tells you there is a one-to-one correspondence between the set of complex number and set of points on the Cartesian plane, is that right? So you have a plane which you draw the graph and everything you learn, but this plane now, instead of having points, you have points, but those points are viewed as a complex number. So all the complex number sitting on the plane, right? So now when you think about the plane, you have every complex number on it, right? And that plane is called complex plane. So we just want to distinguish between your Cartesian plane and the complex plane. But you have one representation. Now think about this. So this is a Pythagorean triangle, right? So what is this? This side is what?
Hypotenuse.
Hypotenuse. What is that? How much if you dip, this is x, this is y. What is
The
this?
square root of x squared plus y squared.
This is square root of x squared plus y squared. Is that right? So in other words, this is actually a distance from the complex number to the origin. Is that right? So which I use as absolute value of z. You know, this is the same notion as you learn in real variable. Always absolute value interpretation of geometrically is the distance, right, from the origin. So this is same thing. So throughout the semester, I'll talk about which are similar with the real variable, which are dissimilar with the real variable, right? So I'll identify those things, which is easier, that you can see that this is the similarity and this is the dissimilarity with the complex variable and real variable. Okay, so the absolute value of z, which is this distance, which is square root of x squared plus y squared, all right? So that's the absolute value of z. And this is sometimes it's also called modulus of z. And this is, what is that? Is the real of z squared plus real of, sorry, I didn't mean that. Imaginary of z squared. Good. So these are all, I'm just trying to combine what you learned so far, right? Okay, so if you look at this representation, this is a Cartesian representation of a complex number, but you can have a polar representation of a complex number, right? So you have this point, but polar representation, you usually write r and theta, is that right? So this is your theta. So this is theta is from the initial axis with this angle, theta. And if you remember that the interplay between the Cartesian coordinate and the polar coordinate. So if you look at what is the sine theta, looking at the triangle, which is opposite over hypotenuse, right? Which is a y over, you can write r, which is the distance. So I wrote that r. So sine theta is y over r, is that right? What is cosine theta?
X over R.
X over r. So that tells you y is r cosine theta and x is r, y is r sine theta, x is r cosine theta, right? So your z, which is the Cartesian form, is x plus y. So now x is r cosine theta plus I r sine theta, which is r cosine theta plus I sine theta, right? So this representation is called polar representation of complex number. Good?
I
So-
did have one question real quick.
Yeah, go ahead.
And I know you're probably going to get to this with the different arguments.
Okay, yeah,
Of all-
yeah. The
We're
little,
going to get to that.
little argument, and I don't want to have a big argument, right?
Uh-huh.
So we'll talk about that.
Okay.
Yeah, that's why I want to pick up this, because I want to make sure that you understand the difference between little argument and big argument, right? Okay, so when you draw a point in the Cartesian plane, x comma y, so that's the unique point, right? Every point has a unique coordinate in it, right? But when you do it in the polar form, then the representation is not unique. So it's not unique. Why is that?
Is this because going around the unit circle, you have to figure out where you're at?
So if I am here, that angle is theta, right?
Uh-huh.
That angle, if I can go once around and come back here, the same angle, right?
Mm-hmm.
But I added 2 pi in it, right? If I go the backward, I subtract 2 pi in it, right?
Mm-hmm.
So the point here has infinitely many representation, right? So this is not unique. So this has an infinitely many representation. So theta plus 2 pi k plus I sine theta plus 2 pi k.
Is it because it's an oscillating function?
Say it again?
Is it because it oscillates? Like when we're talking about it in mathematical terms, would we say it's because it oscillates, or because it's periodic, or because of both?
Yeah. So it's a sine and cosines are oscillatory function or periodic function, right?
Okay.
So that every 2 pi you come back to the same place, right?
Mm-hmm.
So that's why the representation of polar form is not unique, right? So same point, you have infinitely many representation, right? So that's how you write theta plus 2 pi k. Make sense? All right. So, but the idea, here, let me write down. So from here, let me go back here. I'm sorry. The tangent theta is
Y over X.
y over x. So theta is tangent inverse y over x. So I box them because sometimes when you go from polar to Cartesian and Cartesian to polar, so these are the formula you use, right? Now the argument, this theta is called the argument of z, and is denoted by, so theta is little arg of z. So that's a little cheating in the sense that this theta is an argument of z, and then theta plus 2 pi k is also argument of z, right? Okay. But since it is not unique, so I want to make it unique. In complex variable, we want to make it unique. So how I'm going to make it unique? So if I restrict on only theta only on the 4 quadrant, right? So if we say, okay, we only use only first, second, third, fourth quadrant, then my representation will be unique, right? So the question is how you do it. In complex variable, there is always a problem on the negative real axis. So positive real axis and negative real. We'll talk about that as you move on, right? Why there is a problem on the negative real axis. So we want to avoid the negative real axis. So you have the axis. So I want to take this off. I don't want to pass through that, right? So that's why what do we do? We start from here in order to stay on the 4 quadrant. So we start from here, and then this is the third, and then the fourth, and then the first, and that's the second. So this is how we go. So if we start from here, which is negative pi, but I want to avoid that negative pi theta, so less than theta and less than equal to pi. So if I restrict my theta between the 4th quadrant, but this is a little different odd way to do it, because usually we do from 0 to 2 pi, right? But instead of doing 0 to 2 pi, I'm doing here negative pi to pi just to avoid the negative real axis, right? So this theta is called the principal argument. See. Okay. So now we write that principal argument of z is the big argument.
So on our assignment, I know it asked us to find like little argument and big argument. For little argument, can we find anyone? And then for big argument, we need to have it between negative pi and pi.
Yeah, if your assignment asks you to write a representation, right? Then you can choose anything you like in between theta plus minus 2 pi k, right? You can choose anything you like, but I always choose the big argument, right? And then I write 2 plus 2 pi k for the little argument, right? So let me write down the relation between the little argument and the big argument. So little argument is arg of c plus 2 pi k. Okay. So when I ask you to represent one complex number, I'll not terribly mind if you use argument of z, right? Big argument of z. But in general, if you represent a complex number, so you have to write 2 pi k at the end, right? So there are infinitely many representations of a given complex number, right? Okay. Any question? So just a quick example, maybe that will work this out. So here's the example. I'm going to work through it. So just to talk about the little argument and big argument. So I want to represent this complex number in a polar form, and it is given in the Cartesian form. So what is x here? X is,
Negative root 3,
and y is.
-1.
So so which quadrant the complex number is in?
Third.
Third. So that's information is good. So if you really want to picture this, so somewhere here, is that right? So let's find out the representation of this complex number. So tangent theta, which is y over x. So theta is tangent inverse. So this time what I'm going to do, which you have always done in your pre-calculus class, that theta, I want to find the reference angle. You know the reference angle? Reference angle is acute angle, right?
Mm-hmm.
So measure from the positive real axis, right? So what is theta here? Tangent inverse absolute value of y over x, which is -1 negative square root of 3. So it is tangent inverse of 1 over square root of 3, which is equal to, what is
Pi over 6.
pi over 6. So that's the reference angle. So if you look at that, so that's the reference angle. So that's reference angle, and integral geometry, this is also pi over 6, right? Yes.
Or -5 pi over 6.
Yeah. So there are a lot of representation of that, right? I didn't say that this is not pi, this is pi over 6, right? Because this is the reference angle pi over 6, so this is the opposite of that, which is pi over 6, right? This angle.
Mm-hmm.
Nothing to do with pi over 6 or anything. So this is the angle, that's the angle, right? So that means this angle theta, one representation is, this is the straight angle plus pi over 6, right?
So 7 pi over 6.
7 pi over 6. So that's the one representation of that angle, right? And then any multiple of that, right? And then add 2 pi k, right? But if you are looking for capital argument, so as I said, the capital argument only valid in between 4 quadrants. We always start from third, second, third, and fourth. Both of them will be negative, and first and second, both of them will be positive, right? So that means you are here, how much is negative pi, right? This is negative pi, right?
Mm-hmm.
This is negative pi. And now take off pi over 6. You go, how much is that?
Negative 5 pi over 6.
5 pi over 6. So your capital R of C is negative 5 pi over 6. In order to represent your capital argument, you need to use either third, fourth, second, and first. And third and fourth will be always a negative angle because you are going this way. So since this angle will be that angle, which is negative 5 pi over 6. Okay, so now if I want to represent the complex number in one polar form, then what is my R? R is
2.
square root of x squared plus y squared, which is 3 plus 1, which is 2. So this will be 2 cosine theta. So if you have one representation, or anything these are all representation. Okay, so this representation I use 7 pi over 6. This representation I use the argument, the big argument, and these are all representation. So
Dr. Sengupta, what would it be if we had, if it was negative 5 pi over 6 plus 2k pi? Could you write it like that or no? So you wrote 7 pi over 6 plus 2k pi.
you
Yep,
need,
but could we write it also as
Yeah.
like cosine negative 5 pi over 6 plus
this
2k pi?
this number have so many numbers there in it, right?
Okay.
You can add 2 pi, add 4 pi, or subtract 2 pi, subtract 4 pi, and so on, right?
Mhm.
So general representation, if you write 7 pi over 6 plus 2k pi, and if you write negative 5 pi over 6 plus 2k pi, I sine negative 5 pi over 6 plus 2k pi, I'll not be offended, right?
Okay.
I know how to read this. Both the answers are correct, right?
Mhm.
Because when you add 2k pi I, this representation look different, but this will give you all the angle which is here also there, right?
Mhm.
But when I ask you to do a representation using the capital argument, so that will be your answer.
Okay.
But if I ask you, give me one representation of this complex number, I don't care whether you do this, you do that, or anything else, add 2k pi with it, that will be your answer. One representation. So there is no specific answer you have there. Any of them will work because that will represent the same complex number, negative square root of 3 minus r.
Okay.
Okay, any question?
Yeah, Dr. Segunda. So I was kind of confused because you gave us 4 different equations. So which one? Well, I heard you said the second one is a principal argument. So which one would you like? Which one is like the answer you were looking for?
If I try to understand your question, I say I gave you 4 different. Well, this page or the same page?
That page right there.
Oh yeah, okay. All right. So here's the question. Find a polar. This is polar representation of z equal to negative square of 3 minus I. If this is the question, right?
Yes, sir.
Then this is my correct answer. If you write this, this is a correct answer. This is also a correct answer, right?
Mhm.
And there are millions of correct answer based on this 2k pi I, right?
Yes, sir.
And all of them are correct answer. Make
Okay.
sense?
Yes, sir.
But if you want to stick with me, I always do the principal value, right?
Yes, sir.
So always, then it will be easier if you 3 people are there, you write 3 different answer. I have to check 3 things, right? Whether all of them are same.
Mhm.
But if you write negative pi over 6, which is the principal argument, then I'm okay with it, right? It is easier for me to grade.
Okay.
Make sense?
Yes, sir.
So you can use the principal value to represent the theta, right? But you have other choice, infinitely many choices for anyway. Okay. Any other question? Okay. So let me just quickly talk about few properties, because these are the properties we use so often. Properties of absolute value. Absolute values of a complex number. So I think these are the few properties. So these are the few properties of absolute value of complex number. This property is called triangular property. So if you think the complex number, you can also think as a complex number as a vector. So if you think of the complex number as this vector, z1 and z2, then you can apply the triangular property. Triangular property means always the third side is less or equal to the sum of the other 2 sides, right? So you can think that this is sum of the third side, which is the addition of this z1 plus z2. So sum of these is less or equal to absolute value of z1 plus z2. This is a very nice algebraic proof of this. I want you to explore that. You can look at the book. It's nice algebraic proof for the triangular property of the complex number. Do you know how to, just curious, do you know how to prove these? Oh, by the way, this z2 is not equal to 0 because you cannot divide like that. Do you know how to prove any of these?
I mean, I could prove it with just regular numbers, yeah.
No, I mean, see, regular number, specific, not specific number, but because that's not approved, right? You have to do in general. You can do by brute force. Brute force means you write down Z1 and Z2 are two different complex number, right? Then multiply them, take the absolute value, right? And then this is the left side, work the left side, work the right side, and then show them they're equal to each other.
Mm-hmm.
So for example, just quickly, let me just, these are worth doing it.
Can you pull the paper down? Thank you.
So give me a quick multiplication of this. Mhm. So
Like x1 times x2 plus x1 times iy2.
yeah, I'm just writing because complex number I write always the real part and the
Okay.
imaginary part. So I'm using really, don't tell anybody that I'm using the FAL method, right? With the notion that I square is a -1, right?
Mm-hmm.
And then I separate the real part and the imaginary part. So I square is -1. So when I multiply these two, I get negative y1, y2. And then I reverse them, x1, y2 plus x2, y1, right? Yes. So what is the absolute value of this? By definition of the absolute value, it says take the square root of, right? The real part of the complex number square plus imaginary part of the complex number square. So which is x1, x2 minus y1, y2 square plus x1, y2 plus x2, y1 square, right? So which is same thing as what? X1 square, x2 square plus y1 square, y2 square minus 2 x1, x2, y1, y2 plus x1 square, y2 square, x2 square, y1 square plus 2 x1, y2 plus 2 x2, y1. Sorry about that. So I just squared this out, I write down that. It's a lot of work, right? So here I get mistake. X1, Y2, X2, Y1. So this cancel out. So my final answer is X1 square, X1 square, X2 square, plus Y1 square, Y2 square, plus X1 square, Y2 square, plus X2 square, Y1 square.
Can you just move your paper a little bit to the right? Thank you.
Okay. Are you following with me? This is, I'm just doing algebra which you did way back. So I squared this out. This is a binomial. So square of A plus square of B minus 2 times AB. Square of A plus square of B times 2 times AB. And this cancel out, I get that. And that's my left-hand side of that theorem. LHS meant the left-hand side. And then if I do the right-hand side, which is absolute value of Z1 times absolute value of Z2, so you get this one, absolute value of Z1 is X1 square plus Y1 square times X2 square plus Y2 square. And then when I multiply these two right under 1 square root, And then I think you get the same thing what I get earlier. Make sense? I just show you how to do is the absolute value of product up to complex number is the product of their absolute values. Right? You can do the division as well. I mean, because you don't take it granted that this is true unless you check it that whether this is true or not, right? We are in the graduate school, so we want to make sure everything I say, you don't take it as granted. You should just verify them, right? Okay. So you can do for the division, try the division at home for your extra credit. If you need an extra credit, just do the division in the way I just did it, right? It will be a lot of fun doing the division. Okay. I just want to show you now, I mean, I just want to do a little bit proving today. I do all the stuffs in the PowerPoint. I don't show you much proof there. I'm going to show you the same proof using the polar coordinate. And you can see that how easy the proof is instead of going through all those tedious work. So I'm going to show you the same proof using the polar coordinate. So with polar form. So I have Z1, which is a complex number represented as a polar form. And then I have a Z2, which is R2 cosine theta 2 plus I sine theta 2. So these are the two complex numbers. Last time I wrote x1 plus iy1, x2 plus iy2. This is the two complex number. But here, my modulus are different. So R1 is the modulus, right? So what is R1? Just to remind you what is R1. R1 is the absolute value of Z1, right? You know that? The distance from origin to Z1, which is the absolute value, right? Which is R. So same thing here, R2 is the absolute value of Z2. Now I'm going to multiply this Z1 and Z2. So let's multiply. This is fun to do. So when you multiply, you get R1 times R2, and then you multiply these two. Now R1, R2, and then, again, I'm going to use the FOIL method, right? To multiply those two. So you get cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. That's the real part. Plus I, and then you do cross multiplication. So it will give you cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2.
And then we use trig identities, right?
Yes. Now, see, do you remember that you have a sum and difference formula for sine and cosine, right? We never thought that you can apply those things anywhere, right? So here you're applying, this is R1, R2, then you get cosine theta 1 plus theta 2. That's the formula for cosine theta plus I. That's the formula for sine. With me? So I just wrote down the product of the complex number in the polar form. What is the modulus here for the product? What is the modulus for the product of complex number here in this formula?
The R1, R2.
R1, R2. This is the modulus R1 for the complex number Z1. That's the modulus for R2. So the modulus is nothing but the absolute value, right? So, so absolute value of Z1, Z2 is, that's the modulus of Z1, Z2, which is, in this case, is R1, R2, right? But what is R1? R1 is nothing but absolute value of Z1, and R2, which is the absolute value of Z2. I just proved the same property, just like here. That absolute value of product of two complex number is product of their absolute value. Is that right? But this is, I think this is much easier than the other one.
Mm.
And also there is interesting property here. What is the argument here? What is the argument of this complex number? What is the
Theta 1.
theta 1? Argument of this is theta 2, right?
Yes.
You can write as, actually, when you talk about little argument, you can write 2k pi, 2k pi, and all do those things you do, and then still at the end, you'll see that 2k pi and 2k pi. So the argument here, argument of Z1, Z2 is actually what will happen?
Equal to adding them.
Adding them. Oh, amazing. Another property on argument. Argument of Z1, Z2 is argument of Z1 plus argument of Z2. So now look at this. There's a function, argument is a function which take the product of two complex number to sum of two complex number. Is that right? Product goes to addition, right?
Yep.
What kind of power? Have you seen this kind of function before?
With exponents, they do that. And with logarithms.
Logarithm, right? Log of A and B is log of A plus log of
B.
B. Is that right?
Mhm.
So this is, the argument is just like the logarithm function, right? So it takes the addition to multiplication, right? Yeah. So that's just like your in your abstract algebra or modern algebra. So what kind of function takes the addition, multiplication to the addition, right? And here's the one. Here's the logarithm is another one, right? Okay. So similarly, just to close this on, this is again a little work for you to show the division. So argument of Z1 divided by Z2, what will be?
We would subtract if we're going based off logarithms.
So just like the logarithm function, the division takes you to subtraction.
Would the same rule apply with like a power that happens with logarithms?
I'm just, yeah. So power, I don't know exactly what exactly your question is.
So
But-
like argument of Z1 to the third power, would that be equal to 3 times argument Z1?
Yeah, I mean, I don't know what do you mean by 3 power of argument.
So when we take like log
Yeah, and
A,
you're talking about the third property of logarithm, right?
yes.
Yeah, multiplication and so yeah, you can see that, let's see, Zn, right?
Mm-hmm.
Right?
Mm-hmm.
If you have a complex number, you raise to the power n power, how that will happen. Yeah, I mean, let me talk about that. I think you're in there. So let me talk about that to explain how that works, right? So that in order to explain that, let me bring this is you learn already in your pre-calculus card, De Moivre's theorem, right? You learned that before? De Moivre's theorem? No? Pre-cal? Okay, so this is basically the De Moivre's theorem. If you have a complex number, it's nothing to do with the complex number anyway, but you can apply on the complex number. So you have a complex number z equal to r cosine theta plus I sine theta, and this is what probably Erin was talking about. Then if I raise to the power n power, right? So this will be r cosine theta plus I sine theta, and then raise power n. So I messed up. Okay. And this will be r to the power n cosine theta plus I sine theta to the power n. And this is r to the power n. So De Moivre's theorem tells you, this is the De Moivre's theorem. So I should not write that here. So I get cosine n theta plus I sine n theta. So maybe that's similar what you are looking for. So the De Moivre's theorem is this. Okay. Nothing. So if you raise n power of cosine theta plus I sine theta, thinking argument is 1, it doesn't have to be. And then the De Moivre's theorem tells you that if you multiply this complex number n times, which is same thing as multiply the argument by n, is that right? So this is very close to what you were talking about, I guess, right?
Yes, it is. Thank you.
Not exactly. I'm not
Not
happy
ex-
that at
yeah, it's not exactly, but close.
Huh? It's
Not exactly, but close.
but at least this De Moivre's theorem, one of the wonderful theorem in computation, because it saves a lot of computational time, right? Because you are multiplying complex number, let's say n is 100 times, right? Over, and then simple answer is given, right? You just multiply 100 with theta, right? So that makes this is a remarkable theorem. I don't know how many of you knew it earlier, but anything cut down the computation quite a bit. That theorem is a is a wonderful theorem for anybody. Okay, just I'll do one example with you. To apply this De Morgan's theorem. Okay, so here I want to show that 7th power of this complex number is 8 minus 8i. Okay, one way you can do it without knowing De Morgan's theorem, that you can multiply 1 plus I how many times? 7 times.
7 times.
And then you get your answer. I'm sure you get 8 minus 8i. If this changed to 70, then you spend the whole week probably multiply 70 times, right? But if it's 700, then it's out of reach, right? So, but De Morgan's theorem helps you out, doesn't matter what number you have there. So let's do how I can apply De Morgan's theorem. First, I write down this complex number in the polar form. So what is x in this case?
1,
Y is,
1.
so the z, which is r, which is absolute value of z, which is square root of 1
2.
plus 1, which is square root of 2, right? And tangent theta, which is y over x, I take the absolute value, but doesn't make any difference, which is 1. But since this is in the quadrant 1, so your theta will be
Pi over 4.
pi over 4, because tangent pi over 4 in the first quadrant will give you 1. Okay, so now I have my my polar form. R is square root of 2, and then cosine pi over 4 plus I sine pi over 4. Good? I'm going to raise 7 power both sides. So I raise 7 power both sides. So 7 power of square root of 2 is
8 root 2.
8 root 2. And then here I'm going to use the De Morgan's theorem. Since I raised 7 power, my answer will be 7 gets multiplied with the argument. Right?
Mm-hmm.
So I get 8 square root of 2, and then I found out cosine 7 pi over 4. 7 pi over 4 is in which quadrant?
Third or fourth.
Fourth. What is that called?
It's root 2 over 2.
So cosine pi over 7 square root of 2 over 2. And since in the fourth quadrant, this is negative, right?
Mm-hmm.
Minus I square root of 2 over 2. Then I multiply by that. And I end up with 8 minus 8i. So this is just a simple application of De Morgan's theorem, right?
Mm-hmm.
Okay. Any question? Okay, if z is x plus iy, z bar, which is a conjugate of a complex number, right? Which is
X minus IY.
x minus iy. So z bar, if I multiply them together, so I'm multiplying those two together,
X squared plus Y squared.
square plus y square. So z bar is x square plus y square, which is same thing as square root of x square y square o square. I don't know why I write that, right? Is that right? So so this is what? This is absolute value of.
Z squared.
So that means this is one of the property which connects the conjugate with the absolute value, which is useful, very useful property. So absolute value of z square is z times z bar. Good? Okay. So let's do some geometry. So if you look at the two-dimensional plane, you have a lot of different curves there. So some of the standard curves is like a circle, parabola, line, right? And the question is how you are going to represent those graph in terms of the complex number. So that's the goal here, the geometry of the complex number in the complex plane. So for example, real z plus 3 equal to 0. So here, find the graph of these in the complex plane.
So like X equals -3.
So what I do every time I see z, because we are very familiar with x and y, so I change it to x plus iy plus 3 real equal to 0. And then the real part of this complex number is x plus 3 equal to 0. So x is -3, right? So what is this?
A vertical line at -3.
So this is a vertical line. 1, 2, 3. So so that's the graph. Okay, I guess it's all in my PowerPoint. If you have a two complex number, and if you take the absolute value of the difference between them, this is nothing but the distance between z1 and z2. The absolute value tells you what is the distance between z1 and z2, and the way you write the difference between z1 and z2 and take the absolute value, right? So if you understand that definition, what does it tell you here? So Z naught is a fixed complex number, and Z is any complex number. So this tells you the distance from a fixed complex number to any complex number is always a constant, right? What is that definition? Set of all points in the plane which has a fixed distance from a fixed point. That definition is called set of all points in the plane which has a fixed distance from a fixed point. You learn in your algebra class. What does it represent? Describe all the points in the plane which has a fixed distance from a fixed point.
Do you know?
Hmm?
You can try.
So fixed point is,
Is it the reference angle?
say again?
Is it the reference angle?
No, no. I'm asking a question. Describe the all point which has a fixed distance from a fixed point. What is that? Let me elaborate a little bit. Fixed point is the center,
Like the origin, the radius.
and fixed distance is the radius, right?
Mhm.
So which are the points which has a fixed distance from the fixed point? The circle.
The unit circle.
Circle, right?
Hmm.
So here it tells you the distance from Z naught to Z is always fixed, which is equal to R, right?
Hmm.
So let's write down why it is an equation of a circle. This is an equation of a circle.
The x squared plus y squared.
Yeah, equation of circle in complex plane is this: Z minus Z naught. Z naught is a fixed complex number. R is a real number which is fixed. Equation of a circle whose center is at Z naught, which is X naught plus I Y naught, and radius is R. So this is the equation of the circle, and as you see, it's obvious that the distance from a fixed point has a fixed distance from a fixed point is described a circle. So how do you recognize that? That's simple, because Z is X plus IY, Z naught is X naught plus IY naught equal to R. So now I have real part is X minus X naught, and imaginary part is Y minus Y naught equal to R. I'm taking absolute value, so I take the square root of X minus X naught square, which is the real part square, plus imaginary part square equal to R. I don't like the square root, let's get rid of it. So take the square root, square, both sides. So this is the equation of,
The circle for the imaginary plane,
yes.
complex plane.
This is in your pre-calculus class or algebra class. This is the equation of a circle whose center is at X naught and
Y north.
naught, which is nothing but the complex number Z naught, right? And radius is R.
R.
So this is the equation of the circle in complex plane. That's the equation of the circle in the complex plane. That's the equation of the circle in the Cartesian plane, which you learned earlier, right? So I'm making the connection between these two, right? So here is a Z naught, which is X naught plus I Y naught. That's the center, and then this is the radius. Okay. I'll let you go in few minutes. Just a few quick questions, and then
I have a quick question if possible.
yeah, you sure?
So I did the assignment and already turned it in.
Mhm.
And now that we just did this kind of problem, it made me realize one of the questions I represented incorrectly.
Okay. So
In that I solved for x instead of saying it would have been a parabola,
uh-huh.
the equation of a parabola. Is there any way to turn that back in? Or
I'm just okay. When is the last date to submit the homework?
it says till the 6th.
Oh, 6. Okay, so you did it early, right?
Yes.
So what I'll do, I'll clear your submission, okay?
Okay.
Then you resubmit it, right?
Okay.
So hang on your submission for because I started teaching now, right? I'll try to address most of it in the class,
Okay.
because things get now so far nothing is serious here, but it will get serious in few days. So now so far I have done real complex variable. I'm doing still algebra, right?
Mm-hmm.
Yeah. Okay. So look at this. Now if I ask Bay, for example, right? I have to pick somebody. So if I ask Bay, what is this equation for? Here.
The equation for the circle?
Yeah. So if you say circle, then your burden is to give me what is the center, what is the radius.
I'm sorry, what was that?
If you say it's a circle, still you have to tell me what is the center and what is the radius in this equation.
In this equation, then the radius is 5.
Say again? Yeah.
The radius,
I cannot hear you well. Go ahead. One more time.
the radius is 5.
So center is
These 2, 36. Center is it 2 and plus 36i?
there's 36. This is 3i. Sorry.
Oh, okay. 2 plus 3i,
And radius is
5.
okay. So you're almost there. But remember that the standard equation you have a negative sign here, right?
Okay,
But this one is a positive, right?
right.
So that means you have to negate that, right?
So the center would be at -2 and then -3i.
So that's the center, which is the complex number, right?
Right,
And radius is
5.
okay. Good.
Good.
So we'll be bring up so many times circle because when you integrate, you'll be using a lot of circle there because integration over a curve is boils down to integration over a circle. So you need to know the circle well. So here is the equation of the circle. Okay. Okay, I can stop here. If you have any question, you can always write it on the student launch. I like to see there are a lot of questions there. I have a hard time to answer them. I'm just kidding. But I really want you to participate more so that just don't keep it with yourself. I didn't understand this. Just to spill it out, I'll explain. Okay?
Okay.
Be transparent here in the class. So if you want to learn, then you have to be very transparent. Okay?
Okay.
All right. Thank you so much for joining me tonight.
Thank you.
Thank you.
I'll continue doing this unless you get bored and say, I don't want to do it anymore. Okay. So I'll be coming and teaching every night. I want to get back to the teaching. I haven't done that for a year. I took a leave for a year and I did not teach at all. So I really want to go and physically go there and teach every night, but I'm a little scared to go there because I already have COVID and my wife didn't have it, so I don't want her to get it.
Yeah.
So,
So will we have a Zoom meeting then on this coming Wednesday, or are we just meeting on Mondays?
no, I want to do it both days actually, yeah. But if you say, okay, this week is enough, so the PowerPoint I have, this is what I'm going to teach, and I think I already touched on everything, right?
Mm-hmm.
But then I can meet in the next Tuesday. What I'm going to do tomorrow, then I'm going to put the third week work, right? And then I'll teach third week next week, okay?
Okay, so then, our next meeting will be on Monday, and then that'll cover the stuff for the third week.
Yeah.
Okay.
So unless you demand something that, I need more work, so I can come back on Wednesday, okay? Anybody, any single one say that, I can come back on Wednesday, okay?
Okay.
But otherwise, I'll be coming back on Monday, next week.
Okay, on Zoom or in person?
No, Zoom, yeah.
Zoom. Okay, that's what I thought.
Someday I dream about going there, so let's see whether my dream is fulfilled or not. Yeah. But you do a lot of also the Zoom, right? Dr. Alagan teaches Zoom, right?
Not this semester. He's just like doing kind of what you're doing, but without the Zoom. Like have the PowerPoint, and then he has an assignment and
Oh,
quiz.
he is teaching, he's not doing synchronized, right?
Yeah, he's not. It's just the PowerPoint.
Oh, okay, yeah. But I want to teach because I think it is a new course, in entirely, very different course, right?
Hmm.
Yeah, so I really want, because things will be different and conceptually you lose a lot of stuff. So I don't want to do that. At least I have to teach in the Zoom the way I'm doing now.
Okay, that sounds good.
All right. Thank you so much.
Thank you.
All right. Take care, all of you.
Thank you.
Good night.
You too.